Hello, I'm Paul Beckwith. In this video, I'm going to take a sort of top of the atmosphere, high level look at why the Earth is warming and look at how the heat is distributed amongst the different components of the Earth, like how much heat is going into the atmosphere from the total, how much is melting the cryosphere, the sea ice, the glacier ice, how much is heating up the land surfaces going into the permafrost and penetrating deep into the ground, and of course how much is heating up the oceans. And we know that the vast bulk of the energy, the heat energy, is going to heating up the oceans. So basically I'll be talking about the Earth Energy Imbalance. Okay, so if you're at the top of the atmosphere, the imbalance is how much heat is coming in versus how much heat is going out. And clearly, because more heat is coming in than is going out, the Earth is warming. So we're getting the global warming, climate change, and the distribution of this additional heat in the different components and or elements of the Earth system then give rise to changes in circulation patterns in the oceans and in the atmosphere and so on. So in the atmosphere, the jet streams slow down and get wavier, and we get extreme weather events. In the oceans, the ocean currents are actually changing. So if you look at so I'm talking about a peer-reviewed study, and it's part of the global climate observing system work to look at the whole planet and kind of get a system view as to how things are changing. So between 1971 and 2018, the total heat gain of the Earth, so that's incoming solar radiation exceeding outgoing radiation, that difference is leads to a total heat gain of 358 plus or minus 37 Zeta joules. A Zeta joule is 10 to the 21th joules. Of that energy, the oceans are getting about 89% of that heat. Okay, over that time frame, 1971 to 2018. The top 700 meters, 0 to 700 meters is 52%, 0 to 2,000, or 700 to 2,000 meters is 28%, and deeper than 2,000 meters is 9%. So you get the 52 and the 28 and the 9, and that's the 89%. So 89% of that heat gain of the Earth is going into heating up the oceans. Okay, the cryosphere, the ice, the sea ice, the glacier ice on mountains, the glacier ice on Greenland and Antarctica, that's only taking 4% of the total heat gain. 4%. Okay, so imagine now an Arctic without sea ice. So that, that fraction of energy which goes to melting the ice will cause additional heating, a ramping up of the heating in the Arctic, which will completely rewire global atmospheric and ocean patterns. And we're getting to that situation extremely soon. The land is taking up 6% of the total heat gain. Okay, so this is the soils and the permafrost. As you go deeper and deeper into the ground, it's taking up more and more heat at the surface, and that heat is penetrating down into the ground, and that's 6% of the total. The atmosphere, the rising temperatures in the atmosphere, in the troposphere, in particular lower atmosphere, that's only 1% of the total heat gain, and that's a component that affects us the most. That's caused the 1.1 degrees Celsius increase in temperature. That number depends on the baseline, of course, It's more than that. If we go to the 1750 baseline, it's more like 1.4 degrees Celsius. So of that total heat gain, 358 Zeta joules, where Zeta is 10 to the 21th joules, 89% is in the oceans, 4% is in the cryosphere, 6% is in the land, and 1% is in the atmosphere. And in order for us to, that leads to sort of an average, if you look at the rate of change of heat on the surface of the Earth in terms of, watts per square meter, that averages to 0.47 plus or minus 0.1 watts per square meter, and that's from 1971 to 2018. If we take the number, a more recent interval, just from 2010 to 2018, that number goes to 0.87. So most of the heating gain is accelerating rapidly. In order to bring that 0.87 watts per square meter, and that's the square meter is the area of the total Earth, we would need to reduce the CO2 level in the atmosphere by about 57 parts per million. So we'd have to go down from about 410 to about 353 parts per million. 410, I say, it's really more like 415 now. Okay, but that's the sort of thing that we have to do. We have no choice. We have to get to equilibrium in order to halt climate change. And to buy us time to do that, reduce the CO2 in the atmosphere, and we're still pumping huge amounts of greenhouse gases up there. It's all going in the wrong direction at accelerating rates. But, what we need to do is reduce that number to 353 parts per million to get a heat balance, to get the Earth back into equilibrium. So let's look at the paper in great detail here. Okay, so this is what I was explaining. This is the key graphic for this video. Total heat gain, 358 zetajoules, 89% in the oceans, 4% in the cryosphere, 6% in the land, 1% in the atmosphere. That leads to 0.47 watts per square meter heat from over. If you take 358 zetajoules and you divide by, that's joules, watts is joules per second, multiply by 10 to the 21 for the zeta, divide by the number of seconds in that time interval, divide by the surface area of the Earth in square meters, and then you get this number, 0.47 for this time frame. And if we take the most recent decade, almost decade, 2010 to 2018, that number is 0.87. Okay, so we're getting a huge acceleration in the heating of the Earth. In order to get the 0.87 watts per square meter imbalance to zero, we need to remove 57 parts per million. Okay, so this is the key figure. That's the key finding. This is the paper I'm talking about. Just Google heat stored in the Earth system. Where does the energy go? Okay, and it's a great paper, and I'm going to discuss the figures in this paper. It was just published. It was just released, peer-reviewed paper. First of all, these are the SI, the different prefixes. Okay, the symbols. So zeta joule is 10 to the 21th joule. So the 358 zetajoules, you could say it's 0.358 yotajoules. I like that, yota. It should be Yoda, not Yota, yotajoules. But anyway, yotajoules. Okay, this is a global climate observing system that was involved in getting all of the data. You'll notice that there's a huge number of authors on the paper. They're from all over the place, all around the world. It's all part of the world climate, the global climate observing system. And there's a version for the ocean, Global Ocean Observing System. Have a look at these websites. They're fascinating. There's lots of information on them. The Ocean Observing System has thousands of these Argo floats. In Greek mythology, Jason sailed on his ship, the Argo, in search of the Golden Fleece. Okay, so Jason is the Earth observing satellite. So Jason satellites, and Argo is the array of floats. Okay, so let's look at the results of the paper. So here's the results. So you can see that the warming, this is the warming of the ocean. This is ocean heat content in the first 300 meters, first 700 meters, 0 to 2,000 meters, and 700 to 2,000 meters. And you can look compare the period 1960 to 2018 to the period 2010 to 2018. The rate of, in terms of watts per square meter, the power per unit area over this depth range has gone up almost double. From up for the 0 to 300 meter, the layer closest to the surface, the 0 to 700 meter, almost double, 0.7 to 0.4. If you take 0 to 2,000 meters, that's about 6,600 feet. It's up more like 2.5 times, so 1.3 versus 0.5. And if you take the deepest section, 700 to 2,000 meter, it's up about 2.5 times. This is the ocean heat content in joules per square meter for the different depths. So we've got 0 to 300 here. We've got 0 to 700 meter is the blue. We've got 0 to 2,000 meters, and that's the largest rise here. And the 700 to 2,000 meters is the slower rise here. So we've got all of this information on how the heat, so this is how the heat is being distributed in the oceans. Remember, 89% of the heat from that time period, okay, is going into the oceans. This is another way of looking at it. These are the different time periods here. So there's basically 3 study periods: historical, 1960 to 2018. Okay, there's the altimeter era. So if you use a satellite altimeter, measure the distance to the ocean surface, the heat going into the ocean, to expanding the ocean, so you can convert the altimeter data to heat content, heat increase of the ocean. And the golden Argo era, 2005 to 2018, and then the most recent period. So what you can see is 0 to 300 meters. You can see a steady rise in each of these different depth ranges as we go closer to the present. So the last decade has by far the largest ocean heat content increase. 0 to 700 meter, even more. 0 to 2,000 meters, even more here. Okay, so you can see that the ocean is absorbing tremendous amounts of heat. This is the atmospheric component, the atmospheric heat content anomalies. You can see that the variation is much larger in the atmosphere. You know, there's a strong El Nino here, another strong El Nino here, weaker El Ninos and La Ninas here, so there's more fluctuation. And this is just different graphs depicting the same sort of thing. Okay, if we look at the ground, how the land is gaining heat, this is a ground surface heat flux into the ground. So you can see that the ground heat flux is increasing throughout the years. Okay, we can look at this is the global cumulative heat storage within the continental land masses. Okay, since 1960 is the black line, and the confidence interval is the shaded region. Okay, so the heat is going into the oceans. It's going into the ground. This is another depiction of how the heat is going into the oceans here. Okay, so we've got the energy change in Zeta joules from 1960 to 2018 is the last date this data was taken from, and we get the shaded blue line. Light blue line is the ocean, 0 to 300 meter. And I'm going to continue this in another video, so thank you for listening.